Hi everyone. This is the typical spot in which magnetism is typically introduced to students. I chose a different route for my own nefarious purposes. You can just watch the videos in different order if you want, I guess. But this is a slide introducing the Lorentz force. And so basically what we have in this situation is we have a single point charge a single point charge moving through a magnetic field. What happens? And so, if you think back to, two parallel lines of current, one of those lines of current is going to generate a circular magnetic field. The other line of current is fundamentally just a little electrons flying through space. Those electrons interact with the magnetic field and get pulled into the source current. So we know that electric charge in motion interacts with a magnetic field. This is the formula for it, right here. This is called the Lorentz force, and it's basically the charge times its speed times the magnetic field times the sine of the angle between them. So it's a complicated sounding formula, but all those pieces, all those elements are necessary in order to capture what's going on here. We have a charge, it has to be moving through a magnetic field, and it can't just be moving parallel to the magnetic field, it actually has to cut through the magnetic field lines. If a charge is moving parallel with a magnetic field, it won't experience this Lorentz force. But if it's cutting through the magnetic fields, then it will be deflected. And the other thing about this Lorentz force is that it acts in a fashion that's perpendicular to the motion. This is the picture to keep in your mind for the Lorentz force. This formula and this picture go together here. And basically what's happening in this picture is you've got a magnetic field. That's what the four arrows pointing up represent. Imagine a charge flying through this magnetic field. Notice it's not parallel, it's cutting through those field lines. When it does that, basically the angle here is the angle between these two. So if this velocity were up here, the angle is 0. And that's why F would be 0. But in this case, we've got maximum cutting through the field. The speed, the electron, sorry, it's positive charge in this case, so it's protons, say. Protons flying through at a certain speed, and it will be deflected. The force obeys the right-hand rule again. And so basically we have two manifestations of the right-hand rule. One to define the magnetic field, and another to define the Lorentz force. The way to use the right-hand rule in this case is basically take your fingers, point them in the direction of the magnetic field, stick your thumb in the direction that the charge is moving. Your hand, your palm, is going to push in the direction of the magnetic force. Now, this is true for a positive charge. For a negative charge, the force is opposite. Not because the right-hand rule doesn't work, but because the Q flips the F, right? So if this Q is negative, you still use the right-hand rule, but you have to know that it's opposite. It's pointing in the opposite direction. So there's lots of ways to not to trip up on this Lorentz force. Just remember it's basically the right-hand rule, and calculating this angle is associated with the number of lines that are being cut through by that charge as it flies. The other point I should make is that because this force is always perpendicular to the motion of the charge, it's always going to deflect it in the same way that we talked about circular motion. The circular motion, the acceleration of circular motion, is always toward the center of the circle. It doesn't increase or decrease the speed in uniform circular motion. Well, the same thing happens here. Because the force is perpendicular to the motion, we don't actually change the speed, we only change the path. And because we don't change the speed, we don't change the kinetic energy. And so sometimes it's said the magnetic field does no work, and that's true. Even though it produces a force, that force doesn't change the speed, and therefore the kinetic energy stays the same.